All right, we're on to video number 3 for the solids with certain shaped cross sections. In video 1, we looked at squares and semicircles, one going each way. The squares were vertical, semicircles were horizontal. I've got the setups for the answers here on the board and on the screen for you. And in video 2, we actually went and calculated those values in the graphing calculator right here. So I went in detail how to put that in the calculator well and get those answers. Now we're going to look at, in this video, we're going to look at least the next couple here, looking at some different triangle cross sections. So first, what do these look like? So in part C, we're looking at right isosceles triangles with the hypotenuse in the region in S and perpendicular to the x-axis. Okay? So perpendicular to the x-axis means going this way, and the hypotenuse in this region S means that that purple line I just drew, as well as this one, and this little one up here, and this one over here, those are all the hypotenuse of a right triangle, a right isosceles triangle. And the rest of that triangle is like coming out of the board with the right angle vertex at the top. Okay? Now again, my drawing's in 2D there with these active board markers are not super great. So let's look at the Desmos tool to see it. This was the semicircles. Here's the XY plane. We're looking down on it. So at a slight angle here, that's the semicircles. Whoops, don't want it to keep rotating, although that's kind of cool actually too. Let me turn off the semicircle cross section there. And let's go to right isosceles triangles. So the hypotenuse in R, or in S is what we're calling the region, perpendicular to the x-axis. Here is, whoops, I didn't want to do that. Here is the cross section. And you can see that is, it's actually maybe even better from the other side. It's got a couple layers to it there, but that's the right triangle. The right angle is up there at the top, at the vertex, and the hypotenuse is going along the base there, perpendicular to that x-axis. And we can take that cross-section, and we can slide it back and forth through that region S to fill out the full solid, and here is the full solid graphed with it. And so I can, slide that through the solid here, or even animate it so we can watch it for a minute. And again, the idea is that blue wedge there, the integral makes it so there are infinitely many, infinitely narrow little wedges there that come together to make that full solid. All right, so how to compute it? Well, we are perpendicular to that x-axis again. So you want to ask yourself, are we going vertically or horizontally? And we already kind of said, right? If you look over here in the region, it was vertical, right? Perpendicular to the x-axis. The top curve minus the bottom curve, f minus g. This function minus this function is going to give us that distance for the hypotenuse. All right, so then the question is, what is that area, right? Our catchphrase for this type of solid is integrate the cross-sectional area. So what I need to know is when I draw one of those right isosceles triangles, what is its area? There's the minus g, right? That distance is this distance. And I just want to know the area of this figure. Well, if I draw a full square, which is what we did in part A actually, square cross sections, there's one really easy way to see what this is. And that is draw the square and draw both diagonals. And what did I just make? I made 4 right isosceles triangles inside the square. So what that means is this right isosceles triangle, the one that I want, is 1/4 of the square. And that's the coefficient I'm going to use. Now, if you want to see it a little more formally than that, let me go back. And another way to do this, we could find this height here, but easier is probably to find this side, which is the same as this side because it's isosceles. And those would be a base and a height for this triangle since they form a right angle. So on a right isosceles triangle, you should know if you're in calculus class that the side ratios, you probably learned them as x, x, and x radical 2. What that means is, or maybe s, and s radical 2, if I call that hypotenuse, f minus g, if I call it s, then these legs are s divided by the square root of 2. And so if I take both of those, the area of a triangle, of course, is going to be 1/2 times the base times the height. So 1/2 times s over the square root of 2 times the s over the square root of 2. And when we square that, you get s squared on top, and you get 2 on the bottom from that. If you multiply it by the other 1/2, that gives us s squared over 4. And what was, that's that side there. What was s again? It's f minus g. So that's the area of the triangle. It is f minus g quantity squared over 4. All right? So here's what the volume is going to look like. You can see the f minus g quantity squared. That's the cross-sectional area that we're integrating. I'm sorry, that's not all of it. And the over 4, right? F minus g quantity squared with that coefficient of 1/4. And it's with respect to x because we're perpendicular to the x-axis, right? We're f minus g, the width of it is dx of that little cross-section. So we've got dx, we've got x values for the limits of integration, a and b, and it's f minus g because it's y as a function of x minus another y as a function of x. Okay, that's the setup. All right, and the 1/4 is that coefficient that we just found here. The only difference between these different solids, there's two things. There's which direction they're going, horizontally or vertically, and then there's what shape they are. So the horizontally or vertically, again, I've said this before, I'll say it again at the end of the video, it has to do with which differential you use, dx or dy. It has to do with which limits you use, the x values, a and b, or the y values, c and d. And it has to do with which variable is in here, x or y. Those three things hinge on whether it's horizontal or vertical. And then which shape it is only matters about one thing. If it's a square, it's the coefficient, right? So if it's a square, the coefficient is 1, so I don't write anything. If it's a semicircle, we've discovered our coefficient is pi over 8. If it's a right isosceles triangle with the hypotenuse in the region, our coefficient is 1/4. So if you start to know these things, if you know the coefficients and you know how to tell whether it's going horizontally or vertically and what that means, it just becomes so formulaic, so repetitive. All right? So let's go to the next one. A right isosceles triangle with a leg in the region. So instead of this being the hypotenuse, that's going to be a leg of our right isosceles triangle. So let me use a red over top of this. And if I look, this length, again, instead of being the hypotenuse, it is now a leg of my triangle, which means I'm going to make a right angle here and have another leg for the height. And you might be wondering, how do I know if the leg goes on this side or this side? And it doesn't matter. For the overall volume, it's going to be the same either way. And this is going to be the hypotenuse then. And you can probably tell just by looking. This triangle I'm drawing is twice as big as the one we just did, right? And sure enough, it does take up half of the square because I just want this triangle. So it's f minus g is one leg. The other leg is also f minus g. And if you want the area of a triangle, again, it's 1/2 base times height. So it's 1/2 f minus g times f minus g, or 1/2 f minus g squared. That's what it would be if I was going perpendicular to the x-axis, right? Since I'm going perpendicular to the y-axis on this one, we're not going to use f minus g, but it's still going to be curve minus curve. In this case, it's going to be g inverse minus f inverse. And that's going to be our answer on this one. Let's take a look. So we have the 1/2 for the coefficient. We have c to d because it's horizontal, it's perpendicular to the y-axis. We have g inverse minus f inverse. We have the x as a function of y for the rightmost curve minus x as a function of y for the leftmost curve. And then squared, of course, still. And dy, because again, it's horizontal, perpendicular to the y-axis. And so these rectangles for the ith subinterval have a width dy, a tiny change in y. That's the big idea. Okay? I'm going to clear my writing on this page here. And we've got a few different coefficients now. We've got the right isosceles both ways. So let's do one more. Let's do the equilateral triangle. Actually, we'll do all of these because the last two are going to be really quick. The equilateral triangle, perpendicular to the x-axis. So equilateral triangles are different. If you look at the square cross-section from part A, the equilateral triangle having that same side length would fill up part of the square like this. And yeah, we want to know the area of that, right? So if we're doing f minus g for the side length, I need to know what the height is, right? In order to get the area. So if you want to find the height, let's drop an altitude. And when I drop an altitude on an equilateral triangle, I actually make two triangles right next to each other in there. And they're both, think about what they are. I dropped an altitude, so that's that's 90 degrees. These were equilateral triangles, so that means this is a 60-degree angle, and so is this. And this was a 60 up here that I split in half into two 30s. So we just made two 30, 60, 90 triangles. So the height of that, if you know your special right triangle side ratios, which hopefully you do since you're in AP Calculus, then you should know that the height is going to be the hypotenuse times radical 3 over 2. And the hypotenuse is equal to this f minus g. So the height of that triangle is radical 3 over 2 times f minus g, times that side length. Okay? And so, actually, let me write it as just s. We'll put the f minus g in later. Because again, if it's g inverse minus f inverse, it's the same thing, right? So if we call this s and we call this s, then the area of that triangle is just 1/2 times base times height. So it's 1/2 times s times radical 3 over 2 times s, which if you put that all together is the square root of 3 over 4 times s squared. And what's s again? If we're going vertically, s is f minus g, and that's what we're doing here. If we were going horizontally, it would just be g inverse minus f inverse. So our coefficient for equilateral triangle is square root of 3 over 4. Here's what it looks like in our integral. Get the fraction bar to show up there. Okay, and since it's going vertically, these cross sections, it is a to b. For the limits, it is dx. It is f of x minus g of x. One more thing I want to say about this. All these shapes, I drew the equilateral triangle inside of the square. And part of the reason I did that is to emphasize this point. That radical 3 over 4, that square root of 3 over 4, if you take any square and you draw an equilateral triangle inside like this, where one side of the equilateral triangle is the same as one side of the square, the equilateral triangle fills up square root of 3 over 4 of the square. If you put square root of 3 over 4 in your calculator, find it, like turn it into a percentage, that's how much of the square is filled by that equilateral triangle. By the same token, the right isosceles, the right isosceles triangle, I couldn't decide if I wanted to draw a square there or the triangle. I kind of switched in the middle. Right isosceles triangle with the hypotenuse in the region, so with the hypotenuse as the square side, That takes up 1/4 of the square every time, no matter how big we draw it, right? Or the right isosceles triangle with a leg in R takes up half the square every time. And that's why its coefficient is 1/2. And a semicircle, if you make any square and you draw a semicircle inside where the diameter of the semicircle is one side of the square, that semicircle will take up how much of the square? Pi over 8 of it. Okay, that's why these coefficients are there. That's how they relate. With the square, our coefficient is 1 because it's just the side length squared. That's the area formula. With all these other shapes, these coefficients are just how many times as big as the square they are. And so far, all of them are less than the size of the square. So these coefficients are all less than 1. But that's all you got to do. That's the only adjustment that is needed to find these volumes, is to use the right coefficient. That's it. But the next one is actually going to be bigger. We've got a rectangle whose height is 5 times the base. So if the base of the rectangle is there, that's like the side of the square, right? That's the f minus g, or in this case, since we're perpendicular to the y-axis, that's the g inverse minus f inverse, right? Well, if I was doing a square, I would have that same height that I have as base, right? But instead, our height is 5 times the base, so it's got to be 5 squares tall. So this is 5, if this is s, this is 5s. And so the area, of course, is just 5s squared. Our coefficient will be 5. And here's our volume formula. The integral from c to d, because y values, because we're perpendicular to the y-axis, and 5 for the coefficient, and then it's g inverse minus f inverse quantity squared. Okay? I didn't show these on decimals, so I'll show that at the end of this video. I don't have the rectangle ready on there, but I have the 3 different triangles. I have all the different formations of the triangles. I do want to talk about one more thing here, G. I wrote some wackadoodle solid with a cross-sectional area given by A of x. I have seen this on the AP exam before. Sometimes they're good at throwing a curveball at you, asking a question in a different way. And so if you've studied all your different shaped cross-sections really well and memorized them, and you're ready and you go in, and then part D of the question, they throw it at you a little differently, and they tell you S is the base of a solid with cross-sections that are perpendicular to the x-axis given with area given by, and then they give you A of x. And some students will take A of x and they'll try to square it, maybe multiply it by one of these coefficients or something they make up. But go back to our catchphrase. How do you find the volume of any of these solids? You integrate the cross-sectional area. That's what we do. So we just need the cross-sectional area so we can integrate it. And the cross-sectional area was given. It's A of x. So if you know a formula, a function for the cross-sectional area, you only need to integrate that. And since it's perpendicular to the x-axis, then it's going to be dx. It's going to be limits on x, a and b. And that's what it's going to look like. All right, real quick before I end the video here, let's look at the right isosceles triangle with the hypotenuse in S perpendicular to the x-axis. So, I did do that one. Hypotenuse in R perpendicular to the x-axis. All right, let's look at the leg in R, this time perpendicular to the y-axis. Perpendicular y-axis, so that's horizontal, leg in R, horizontal. And you can have the leg on the right or the left. Here's what it would look like, with the leg on the right side. So you can see the solid. That wall on the right side is a little sketchy. You can a little translucent. But here, let's eliminate the solid for a second and just look at the cross-section. So that's with the leg on the right side of the solid. This one would be with a leg on the left side of the solid. I guess I should turn the other one off. And it doesn't matter for the volume which one you do. They're going to come out the same. They'll look a little different, I guess, but it'll come out the same either way in terms of the volume. And so that's what that looks like. Okay. And then let's also look at the equilateral triangle. And I think that one we had perpendicular to the x-axis. So here's our cross-section. We can just kind of slide that through the region, right? Whoops. There's that here. Let's animate it. And turn on the full solid. And so that's what that one looks like. Okay. If we want to compute these on the calculator, it's really the same as we did before. It's just a matter. I would just say if you need help with that, watch that second video where I do it for the squares and the semicircles and just apply the same thing but with a different coefficient. That's it.